Okay, so I'm going to talk about um the linear programming duality concept, and I'm going to be using this for something that is very useful in game theory, and it's the equivalence between maximization and mini-maximization. So first off, let me give you the setup. The setup is that you have a matrix A which has only positive entries, and we want to solve this problem, which is uh, maximize over x and minimize over y, this quantity x transpose A by. Once again, A is a matrix with all positive entries. And what are x and y? So x and y are probability distributions essentially. That is that all of their entries are positive, so all y sub j are positive. At the same time, their summation is 1. Similarly for x, x sub I is all positive, and summation of xi is 1. Okay, and we want to solve this problem. At the same time, we also want to solve this problem. So minimize over y, maximize over x, x transpose ay. Once again, under these constraints. So the first thing that I'll do is that I'll rewrite these problems in a way that is better. So firstly, notice that given a y, maximizing this quantity uh, through the probability distribution x, that's more or less just finding the biggest value in the vector a y. So this is just the maximum value in the vector a y for a given y value, and we minimize that over y. So this problem is exactly the same thing as that, and this is, I think, easy to prove because essentially we're just doing something like just picking basically a weighted average of the entries in a y vector, because once again x is something that's like a probability distribution. So it's like the weights. It's the weights for some sort of a weighted average, right? Yeah. um, so then x transpose ay is obviously just the dot product of x and ay, the vectors. So the coefficient of x sub I would just be ay sub I, right? So if you had to imagine, this is just a weighted sum, and then we know that by the power mean inequality, what's going to happen is that the maximum value is what we are going to go for. Yes. Okay, cool. That's amazing. So yeah, instead of power mean inequality, you can think of that as the L0 and L1 norm and all that stuff. But in the end, the point is that this can be written like this thing. Similarly, this can be written like this: minimize over j of x transpose a sub j, or if you like, a transpose x sub j. So the jth entry in the vector a transpose x. All right. So once again, all of this is, so now you still have to have these constraints. So these constraints are going to go for this problem, and this is going to go for that problem. And now we want to show that these two are the same problem. So first what I'll do is that I'll rewrite both of these problems somewhat differently once again. So this problem can be written as, so we just think of this whole thing as just some quantity z. So maximize z basically, where z is something that is less than or equal to the minimum of these entries. So it should be less than or equal to each of the entries in the a transpose x vector. So you just have z is less than or equal to a transpose x sub j for all j, right? and then you still have these constraints, so x sub I are all bigger than 0, so bigger than or equal to essentially, and the summation of xi is 1, right? So we have we have changed this problem into a nicer form, nicer for linear programming essentially. What about this one? So once again we can do the same thing. We can say minimize over y. Let's call this whole thing as w. So we'll just call this w. And now we have to have that this is the maximum, right? So it should be bigger than or equal to each of the entries. So it's just a y sub I. At the same time, you also have these other constraints. Y sub j is bigger than or equal to 0 for all j, and summation of y sub j is equal to 1. All right. So these are our problems. Now we want to transform the upper problem into the lower problem. That's our goal. Okay, so let's start. First, what we'll do is that we'll linear combine all of these things so that we can have some sort of an upper bound on z, and then we'll try to reduce that upper bound, and then we'll get the solution. Yes. Okay. So basically the idea is something like, if there is an x vector such that this problem is solved, right? Let's call it x star. Then for that, what must also happen is that there must be some sort of combination, right? So that if there's a unique vector like that, then there must also be some sort of linear combination of all of these inequalities which bounds z, so which upper bounds z, and that upper bounds value for x star is what the z's value will be, right? So that will be the solution for the problem. Okay, so what I'm going to do is multiply each of these inequalities by some factor, which I'll just write as yi. So it's basically yi times z, right, is less than or equal to yi times A transpose x sub j, and this is true for all. So I should actually write it as yj, sorry. So for each of the jth equations, I'll write this thing. So this is for all j, obviously, where yj is bigger than or equal to 0, right? At the same time, I'll also multiply this equation in a nice fashion. So I'll put the summation of xi to the right hand side. So I'll just have summation of x sub I, or if you don't want that, what you can do is you can write this as 1 basically. So the 1 vector dotted with x vector, right, and that is equal to 1, right? Cool. Okay, so let's put this inequality on the side for now. Okay, and what now I'll do is just I'll add all of this up, and so what I'll get is summation of yjz, and I also will put a negative over here just for the fun. But yeah, so just summation of yj minus 1. I shouldn't do it like this. So summation of yj times z minus 1. Okay, so what I'm going to instead do is not multiply this by 1, but rather let's just say something like w. So we'll call this w over here, and so this will be w vector, which is basically just like w times 1 vector, but I hope that makes sense, right? So this will just be what? We'll add all of this up, so this just becomes summation of yj A transpose x sub j, and then minus w vector dot x vector, right? This is less than or equal to, sorry, yes. So you can clearly see this just becomes so you can write this whole thing as just summation yj. You can write this whole thing as, it's supposed to be w over there, sorry. So it's just summation of yj times z minus w is less than or equal to this quantity. But once again, now what's summation of yj a transpose x sub j? That's exactly the same thing as the dot product of y vector and a transpose x, which you know is just x transpose ay. So I just took a transpose on a transpose x and then multiplied by y. And yeah, and over here as well I can write this as minus x transpose w or minus x transpose 1 vector, right? And that stuff times w. But then this whole thing can just be written as x transpose times this matrix, so it's just ay, that vector, minus w times 1 vector, right? So what we have written so far is that this equation, yeah, is true. Okay, so now we can rewrite this thing as, so first what we can do is we can impose some really nice sort of constraint on this, which is to say that summation of yi should be equal to 1. The reason we are doing that is, well, yi is already positive and stuff, right? So we can just divide this whole thing by summation yi to make this 1, thus normalizing the whole thing. Yeah, and then you just have another w which is also positive quantity or something, and then yeah, so just, you know, nothing much really changes. So instead of doing all of that, what we could do is just, well, directly say, well, just make summation of yi equal to 1, like that. That does exactly the same thing. So imposing that, what you will have is that this thing is somehow gone now, like summation of yi is just 1, right? Summation of yj, that is. So you have this stuff, summation of yj equal to 1. At the same time, you also obviously have yj is positive and obviously w is positive. Yes. So these are our inequalities that we have so far put down, right? Like imposed on this. Now, so once again, just this stuff is of our own choosing. Like nobody told us to be doing this, right? So we can certainly impose inequalities like that. Okay. So let's just delete all that. So I'm just gonna write the final equation essentially. So the final equation just boils down to this thing, that, you know, z minus w is less than or equal to x transpose a y minus w and 1 vector, which we can rewrite as z minus, or you could just say that directly, like and never mind that. So it's just z minus, so z minus x transpose times all of this stuff, or you could say z plus w 1 vector minus ay x transpose. So you could just think of a dot product over here, dot x, yeah, that thing is less than or equal to w, right? Okay, so what we essentially did, and obviously yeah, okay, so that's fine so far. So what we essentially did is that we bounded something which is a function of x and z by some quantity called w. Now what we can do is we can show that z is less than or equal to this thing by imposing another condition, and that condition would be that all of these quantities must be negative or 0. If that happens, since x are all positive, z will be just less than or equal to this quantity. Sorry, all of these should be 0 or positive. That's what I wanted to say. Then z will be less than or equal to this quantity, and then you really just have z is less than or equal to w, right? So then we just minimize w and you get some sort of an upper bound on z, right? Okay, so that imposing that would go like this, that you would just have, let's just think of the you know, jth entry, or let's say the ith entry, because x is a vector with I as the index. So just think of the ith entry of this thing, that's the coefficient of xi. Obviously we want that to be greater than or equal to 0. So what we have is that w, because the ith entry of one vector is obviously just, well, yeah, just 1. So w minus ay sub I, that has to be greater than or equal to 0. At the same time, what we want is that we want to minimize w, right? So this thing can be written as W is greater than or equal to this quantity directly, no need for this stuff, right? So then, yeah, so we minimize W, and then what we can show is that whatever is the solution of this thing, call that Z star, that thing is less than or equal to W star. I mean, we just showed that really, like, because Z is less than or equal to this stuff which is less than or equal to W. So the solution of this thing will be bounded by W star, and that's called weak duality basically. So what you have is that if you solve this problem, minimize W under all of these constraints, we remove all of this obviously. Under these constraints, that summation of yj is equal to 1, yj are all positive or equal to 0, and W is obviously positive, but like that doesn't really matter because this stuff is obviously greater than or equal to 0 in any case. So yeah, and W is greater than or equal to this for like all I, which is by the way already greater than or equal to 0, so you could erase that inequality. And we want to minimize W, right? So if you solve this problem, you get the minimum value of W star, that will be greater than or equal to Z star, which is the maximum value of Z from this problem. And would you look at that, this is exactly the same thing as this problem, right? To minimize W over some vector Y, or just don't have that over there, okay? We just minimize W under these constraints, that W should be greater than or equal to AY sub I, yep, for all I obviously, and summation of Wj equal to 1, yes, and Yj are all, so summation of Yj equal to 1, and Yj are all positive or equal to 0, yes. Cool. And so what we have just proved is that these two are the same problems. Now what strong duality says is that if there is a solution to this problem, right, there's an optimum solution, in that case that will be exactly the same thing as this guy's solution, that is to say that Z star will be equal to W star. Alright, cool. So that's pretty much it. That's all I wanted to say, and I'll see you guys in the next video.